So I'll try and give you a little bit of perspective. Nick asked me to be a little bit broad and highlight a couple of things rather than go very deep in one particular topic. But I'll try and give you some perspective on challenges that we see in wireless networks from different angles, and give a little bit of flavor of some of the activities that are going on currently in Bell Labs, specifically in my department, and also a little bit outside where we're collaborating with other people and other organizations, whether in industry or academia, around the topic of green networks. So since Nick said that this is a diverse audience, maybe I should hope that you guys think that wireless is not that trivial, and maybe I'll try and convince you there are actually real challenges, and it's not just don't install wires and everything's done. So hopefully if you're working on wireless, you're convinced that this is hard. If you're not working on wireless, maybe this becomes exciting and you're interested in working on wireless. Let me just, I'll briefly talk a little bit about AlcatelLucent and Bell Labs, and I'm not sure how much all of you are familiar with Bell Labs or AlcatelLucent, and so I'll have to put my little plug in for the company. Then I'll talk a little bit about next generation wireless networks in general. I'll talk a little bit about the trends that are happening in the industry from the device, from the application, from the traffic perspective. And I really want to give you some ideas of what that means for the network and how we can deal with some of the challenges that are created by all the great things we like called iPhone and iPad and so forth. And then I'll spend some time on the energy efficiency, and it's part of the overall big picture, but I'll focus a little bit more on the energy efficiency. Right? So AlcatelLucent was created in late 2006 at the time, merging Alcatel from France and Lucent Technologies. And Ben Verwaayen is the CEO now of the company. We're actually a French company, headquartered in Paris. Here are some numbers, fast facts from 2010. Most of that is probably still applicable. Just a couple of weeks back, or last week, we announced results for 2011, and they were actually pretty positive, and so a lot of good things happening there. One thing that's notable is the number of active patents, so we're very active. We're driving that a lot from the Bell Labs side, as well as some of the business unit R&D teams, that we really do focus a lot on the R&D. We do focus on the patent side, and we do focus on coming up with innovative solutions that make a difference in the products, and that's kind of the mission of Bell Labs. And broadly speaking, we're a very diverse company. We look at all aspects in networking, which may set us apart from some of the other big competitors. That we do have a lot of business in the wireless side. Chances are that if you have a Verizon, AT&T, or Sprint phone, you're talking to one of our base stations right now. There's probably a 1 in 2 chance that your phone is talking to some of our equipment somewhere. We have a pretty big business in the IP router space, the edge routers, the core routers. We also market leading in DSL, PON, so if you have fiber to the home, chances are it's also some of our equipment. And then we have a whole services organization and so forth. So we're really kind of trying to span the overall end-to-end picture so that we can offer these end-to-end solutions to the customers and not just be in certain areas. So roughly from 2010, Lucent was very heavily focused on the US side. Alcatel was very heavily focused on the European side. So one of the reasons for the merger was really to create a global company with global reach, with ideally a third of the business coming from North America, a third from Europe, and a third from APAC. And so that's not 2010. These are the 2010 numbers. You can probably expect APAC numbers to grow and might even become the biggest region, primarily driven by India and China, and a lot of developments there. So when you look at Bell Labs Research particular, Bell Labs includes the corporate CTO office, as well as the intellectual property division, as well as a chief scientist office, which is actually responsible a bit for university collaborations and so forth. But Bell Labs Research right now is about 900 people, 900 researchers in 8 locations. A quarter of those are in the US, pretty much exclusively in New Jersey, a quarter in France, and then we have locations in Germany, Ireland, Belgium, India, Korea, and China. And those other locations are a little bit smaller, but we're still very much the way you think of Bell Labs from the past, but maybe some tweaks to increase focus and speed in the research compared to maybe some of the things we did in 5-10 years back. So this is the last slide as a plug on the company. So some of the things that you may know about but may not necessarily associate with Bell Labs. So Bell Labs history goes back to 1925, and some of the things that came out of the labs are sound movies, who actually won, I believe, a Grammy for the sound, the work on sound movies. Radio astronomy, most famously the transistor. Shannon actually, I think, was in the labs when he wrote his 1948 paper on information theory. Solar cells, which are maybe becoming again more important, for in the green space. Although we're not in the solar cell business, but solar cells were invented at the labs. The laser, you're all probably using Unix or C in some shape or form. So Unix was invented in the labs in 1974. Actually, sadly, Dennis Ritchie, who was one of the two inventors of C and Unix, he passed away a couple months back, and his office is actually right across from the hallway from mine. So then, general DSPs, DWM, Raman amplification, BLAST, which I think Burr is quite familiar with. More recently, and things that I've been involved in are the BSR, which is a base station router architecture, is looking at collapsing a lot of the radio network functionalities into smaller devices and co-locating a lot of functionality. And that actually was one of the things I worked on, which was really a motivation for the venture that you mentioned, that when you want to deploy these networks very quickly, you want to look at integrating a lot of the functionality. So a lot of the research work then ultimately found an outlet in this venture. And then very recently, last year, we announced something like Light Radio, which is really changing a little bit how you build networks and how you deploy networks. And this was also coming out of Bell Labs a couple of years back. So let me go to a little bit what I see going on. And we always worked on data, and it was always about increasing the data throughput and doing mobile data, and this started way back even when I started. It was all about how do we do energy efficient wireless data, how do we do scheduling, how do we do power control and all that. But it never really took off, and some of the applications and some of the use cases were a little bit artificial. And I remember one of the examples that we talked about way back was mobile data is used by insurance agents when they come to your house, that they have the laptop with a little dongle and they download the form that you have to fill in, and they fill it in, and then they upload it again. Well, that's okay, but that's not really driving the volume that now you have with iPhones. And so I think the iPhone really turned 3G into reality and really made us aware of what was going on, and really drove the demand. And we're always looking for the killer app, but maybe it wasn't the killer app, it was the killer device. And and that trend will definitely continue. We see the iPad and maybe the Apple TV or what else comes next. That will just continue driving the demand up. I had to plug this in this morning. I'm not sure if you've seen this one. This is from this morning, and I couldn't resist putting it in. You can read that, right? Okay, so then what is really going on? And maybe let me ask you this question to you and see if anybody wants to react to it. What is really the difference between a phone, a tablet, a laptop, and a TV? And if you think about how we use these different things, in the past, the phone used to do the phone, you make your voice calls on it, and that's it. Your computer was what you used at home or in the office. You had your laptop when you went to a conference, or maybe when you went on vacation, you want to take your laptop. You had your TV, and you did a particular set of things with the TV. And now it's very different. You want to use everything on every device. So my answer to that question, actually, let me not give it. Anybody want to answer that question on what's the difference between these different devices?
Level of portability.
I'm sorry?
Portability.
Other than the TV, they're all pretty portable. In what sense, data consumption? Volume or?
Between the laptop versus the smaller devices right now.
Okay, so think a few years out.
User interface.
Okay.
Processing power.
Okay. I think it's just the screen size. I think the user interface is, the interface on the phone and the laptop and the tablet is the same. I'm not sure you actually swipe on a TV, maybe not, but to me the biggest thing will just be the size of the screen, maybe the processing power, because now you want to do more high-resolution video on your TV than on your phone, and maybe that you require more processing. But I think you'll end up doing all the same things on. You might just talk to your TV in the future. You don't have a phone. You just talk to your TV. You just watch a show and saying, "Hey, call Nick. the TV dials you and says, hey, did you see this show? Switch to that channel, watch the game, or whatever. That more and more you're starting to use the same devices, the different devices for the same things. You do all the apps on the TV. You do all the same apps on the iPad. You start putting some of these apps now in embedded devices in the car. So it's maybe a little bit provocative, but I'm predicting that 5, 10 years, maybe 10 years from now, we won't really see a difference in the device in terms of what we do. They might have the quality of the delivery of the medium might be different, and because of that, the processing power, the memory might be different. But in terms of what we want to do on the devices, I don't think will be very different. And although I work in maybe a high-tech field, I still had the old TV that I bought when I moved to New Jersey 11 years ago. And when the Patriots finally made it, so I still have my Boston affiliations. When the Patriots made it to a Super Bowl this year, I decided to buy a new TV. And oh gosh, I got the one that has Facebook on the TV. So now when I'm doing my Facebook updates, I have like the TV on one side and Facebook on the other side. And I was like, I had the guys when they delivered the TV like, oh my God, you're kidding me, the old stuff you had. But so it's kind of that thing that now it made me really think about. I'm working on this stuff to make this happen, but I'm not really using it. I got a BlackBerry and I have an iPad, but I'm generally not really pushing getting the latest version of the iPhone and so forth. But I think we're really starting to use the different devices more and more for the same things, and it's blending between what you do on the phone, what you do on the tablet, what you do on the laptop, what you do on TV. It's really just all kind of coming together, and that obviously has huge implications for anybody generating content, anybody delivering content, because we want to consume it in very new ways. And even when you talk to companies like HBO and Universal, what does it mean to them that they have to deliver premium content now to not just your TV, but also your tablet and your phone? What does that do to them? And for us as network providers and then the service providers, what does it do to them, and how do they need to change their business models? How do they need to change their network designs and their network operations to make this happen? So there's a strong trend, I think, on the device side. At the same time, we have certain expectations from the applications we want to run and our applications. I really want this always-on experience. I really want to be able to access any content, anywhere, anytime, any device. I'm not happy anymore with saying, I want to make a phone call now, but I need to send you an email, or I'll wait until I'm home or I'm at the office. I want to send it now. I want to send it now. So we're actually driving a lot of, with our expectations, and maybe with seeing some of the things actually happening in the real networks, we get greedy and we demand more. So we always want to have faster access, access to everything. I want all my data to be available to me anytime, wherever I go. I should be able to see all my files that are stored in an AlcatelLucent server in New Jersey. I want to see that right now and so forth. Right? So the combination of user expectations and devices and applications is just really driving a lot of traffic growth and underlying network changes. Okay? So when we talk about applications, what applications do I think about? I still think that voice is really important. You still have to make very reliable voice. We still complain about the voice quality, although we've kind of accepted the current quality. But I think still voice remains very, very important. And there are probably a lot of applications where it's not necessarily making the voice call, but it's the voice becomes the interface to the device and to the application and to the network, that I don't want to have to dial things. I don't want to have to type in requests, but I want to just talk to the device. I just want to talk to my laptop. I want to talk to my tablet, and saying, Siri is kind of the starting point of that. But how do you make that even bigger? How do you make that more generally applicable, not just within the iPhone? Mobile video, everybody's talking about mobile video, and this is as much the conversational video, the streaming video, the YouTube, the mobile TV, all the video conferencing. So there's no doubt that mobile video is really the main bandwidth driver, really driving a lot of the traffic growth from a data volume. It's really mobile video driving it. We see a lot more multimedia social networking. Social networking, Facebook and LinkedIn are not just little updates, but now more and more you integrate Facebook working with Skype. Google Plus, you see a lot more the multimedia part being integrated into the social networking, which then also drives, again, the mobile video. The one area that we haven't really talked too much about in general, I think, is machine to machine, and what machine to machine and all the sensor communication, what that does to the network. And there's some predictions that by 2020 or so, we'll have 50 billion devices on the internet. Billion with a B. So what does that do to the network? And probably it doesn't do very much from a data perspective, from the actual data volume, because all these devices will just send a kilobyte or 2 kilobytes of data. But now you have a really large number of devices trying to access the network, and that might just completely disrupt the network from the signaling perspective and completely bring the networks down. So how do we build networks if you actually get to even 10 billion devices? How do we handle that? And then, of course, there's a lot more applications. I think if we'd given this talk 5 years ago, 10 years ago, probably wouldn't list these. So some of the new areas that are coming up is everything around smart X and intelligent applications. It's smart education, a lot in telemedicine, connected healthcare, your heart rate monitor, how do you remotely talk to your doctor, how do you get the remote diagnosis done. A lot of cost savings in the medical field are through remote and telemedicine. Mobile payments, connected commerce, anything related to intelligent transportation. This is not just doing all the things we want to do on the tablet and the phone inside the car, but this is also car-to-car and car-to-infrastructure communication of how do we make transportation itself more efficient. Everything with logistics and fleet tracking, that's probably the first area where machine-to-machine and sensor communication really got started. Then you have everything around smart homes, smart buildings. A lot of this is driven by energy management. That ties into smart grid, also ties into connected consumer devices. So that's an example there is you have sensors in your house that detect when you leave, that look at when it's cheapest to do your laundry and automatically start your washing machine and so forth. And then you get the little bit crazier stuff of your fridge talking to your toaster, talking to the grocery store to order food and so forth. So there's a lot in all of these spaces. None of them have really taken off at this point, but a lot of these areas are really predicted to grow very, very rapidly in the next 5 to 10 years or so. And they will, I believe they will really disrupt the network architectures. Okay? So on this slide, I have some numbers just to give you, when I talk about large growth and big volume, what are sort of the numbers that we're talking about here? These are some predictions. On the left side, you see between 2010 and 2015, the number of petabytes per month broken down by dongles, tablets, smartphones, and feature phones. And what's really important that we see a 30x growth over 5 years. This is just in the mobile space. So that gets you to roughly the factor 1,000 over 10 years that we talked about yesterday. When you look at the internet in general, it's probably a 30x growth over 10 years. The mobile space will grow about 30x over 5 years. Right now, about 80 to 85% of packet switch calls already originated on smartphones. 40% of 3G devices are smartphones, and that will just increase with more devices coming out and more people getting these devices. So this is broken down by the different devices. If you look at how the traffic is broken down by applications, you'll see here this light blue area is mobile video. So that's really predicted to be the dominant piece already right now and predicted to be even more dominant in the future. You have mobile web data, you have mobile peer-to-peer, and then you have gaming and VoIP. So this is not in terms of number of connections or number of sessions. This is really in terms of terabyte per month, so raw data. And what this doesn't show is the machine to machine. And we've done some analysis looking at certain areas that I had on the previous chart for the Smart X applications and looking at the New York metropolitan market. And that total market might just generate about 16 megabytes of data per month for the metropolitan market, right? So from the actual data perspective, it's not that big. But when you looked at the signaling, it could be up to 40% of your signaling load. Right? So because every time, if you look at the current architecture, every time you send 1,000 bytes, you initiate a connection. And you allocate resources for the connection. You block resources and you're sending 1,000 bytes and you tear it down again. So you have a lot of the signaling delays and the setups and so forth that could really just really kill you. The bottom right chart, so this is definitely a problem in terms of how do we need to grow networks, how do we need to scale networks to handle this kind of traffic. The flip side, if you look at the cost and revenue structure, is shown in this bottom right chart. The yellow curve at the top shows the growth of worldwide voice revenues, So that's growing a little bit, but roughly flat. The green curve shows worldwide data revenues growing a little bit more rapidly, but the purple curve is showing the growth rate in traffic. So now if you're an operator, you have to support this growth. And as an operator, you want to support that. As a consumer, we want this. But your revenue is not growing. So this is not sustainable. And this is then ultimately where you see things like tiered pricing and new pricing models come into play that operators want to try and solve really this problem. It also goes to how do I build networks that transport this traffic in a more energy efficient way so that the cost doesn't go up this much. And then the cost is broken down by CapEx and OpEx and so forth. So there are different numbers to look at there. Okay. So from a technical perspective, what are some of the really big challenges in wireless networks, and what are some of the limitations that really prevent us from just scaling this stuff up? Well, for one, we have limited frequency spectrum. That's allocated by the FCC, so the carriers have to buy the spectrum. It's allocated. You get into, and that's really limited. They own it, and they pay huge amounts of money for that spectrum. And because of that, you see a lot more work now in white space, where people try and be creative. It's not just, even the carriers are thinking about white space, where they get into this unlicensed spectrum. Wi-Fi is a tremendous opportunity because it's the unlicensed spectrum. And when people realize that they're really running out of capacity, that's when people, even operators and equipment providers, we're starting to think about white space and as another dimension of addressing these limitations. From a fundamental perspective, we're actually getting pretty close to fundamental limits. So maybe we're a couple dB or so away from the fundamental limits. So you're not going to change the fundamental limits, but you have to change the game. And several years back, when you get to the fundamental limits of a point-to-point channel, then we look at MIMO came about because of that. We're looking at multi-hopping. We're looking at peer-to-peer. So there's different things that are then ultimately driven by these limitations, where people are trying to find other ways to solve these problems and address limitations. Fundamentally, the wireless medium is a bad medium. You're going over the air. You have a huge propagation loss. Some of the things that make wireless great, that one person can talk to multiple people, is also making the medium bad in the sense that if multiple people talk, they create interference with each other. So it's a much tougher medium to deal with than fiber optics, for example. It's energy intensive, partially because the medium is tough and you have a lot of propagation losses. So one way to overcome that is to increase your power so you overcome the propagation losses. And I'll talk more about that towards the end. And then finally, you have deployment constraints. People more and more don't like the big towers and big equipment that's really obstructing the landscape. So you'll also have deployment constraints that may not come from the actual technology, but may come from regulators, from zoning regulations, from townships that really put constraints on where you can deploy and so forth. So that also forces a little bit of some of the new thinking on how you deploy networks and maybe go to small cells, maybe don't go to the macro cells and so forth, because it might be a way of getting around these deployment constraints. Okay, so one of the things we're looking at that's quite promising, and I'll try and hang off the middle portion of the talk off of this whole topic of heterogeneous network architectures, and I think of heterogeneous network architectures in two ways. It could be the same technology, but you have different layers. You have macro coverage areas, you have small micro coverage areas, you have femto coverage areas. So it's one access technology, whether it's Wi-Fi or 3G or 4G, but you have different layers in that architecture. But it could also go across technologies. So you could have a network that has a 3G and 4G combination, has a 3G, 4G Wi-Fi combination, and so forth. So this is maybe a picture of a network in the future where you would start with some large 3G, 4G macro coverage areas that give you large capacity and primarily for coverage reasons give you large coverage areas. But then you have downtown areas, you have these metro cells that have smaller coverage area but give you a really high boost on capacity where you have traffic hotspots and so forth. You may have your Wi-Fi. Enterprise may have enterprise small cells. So think of those as metro cells but indoors for enterprise purposes. And then you have your femto cells, your residential small cells. So the network will be a combination of different layers, different technologies, and the goal will be really to try and squeeze as much capacity out of the different layers and different technologies, and I'll talk more about how we think about that. Het nets have sort of a potential to increase the overall network capacity by 1 to 3 orders of magnitude. Well, 1 to 3x, I should say. But of course, if you start deploying this compared to a network that was only macro cells, you have a lot more complexity, because now you need to figure out more where you deploy these different nodes. You need to engineer it differently. You're deploying more nodes to start with, so you get into a lot of complexity from the deployment, from the operation side, from the management side, and it's just not practical to do this manually or by technicians doing drive tests and manually configuring nodes. So this really drives a lot of automation into the network. See, how do we deploy hundreds, thousands of nodes in relatively small areas? So you get a lot of work around what's called self-organizing networks. And there are good reasons to do it, even in macro networks. If the network is self-organizing autonomous, you're really saving time-consuming and repetitive tasks, which then time-consuming and repetitive usually translates into high cost. You can avoid drive tests. You have the network configure itself. You simplify your time you shorten your time for deployment of the network. You can more quickly adapt to real-time changes in the network, because once you measure it, you realize you have a change in the network. Then you have to send somebody out to make the changes in the network. That change may not be relevant anymore and may have gone away. So you want the fast iteration on the network performance to really get the most performance out of the network. And then ultimately, this should translate into higher quality of the network, higher user experience, more throughput, better end user experience, because that's ultimately the end goal, because that's the one goal that really translates into money for the service providers. So a lot of the work in SON is really driving intelligence and automation into the networks to help solve some of the problems that are inherent in networks, but also solve some of the new problems that are created because we go to these more complex and more diverse networks. Okay, so this is not meant to be an exhaustive list of all the technical challenges, but maybe just a pointer to some of the areas, and some of these are addressed, some are not. So this is maybe also just a pointer for you guys to think about what might be different areas to think about and maybe do more work. I tried to categorize them in 4 big categories. Maybe the first one is just around the base station and the network element. So this is anything that solely deals with one single base station. How do I automatically configure that? How do I make sure that if I deploy a base station, I can simply just plug it into a network and it will work? I don't have to do drive tests. I don't have to do any manual processes. It's just plug and play. How do I automatically provision radio parameters? How do I provision handover parameters? And anything that's really local to the base station to improve capacity. Then you get into things that span the larger network, the collection of base stations in the radio access network. And again, that starts with even where do you place the cells? Are there smart ways of figuring out where you should place the cells? How many should you place? What frequency do you operate them? Do you need to really plan that, or can you just randomly sprinkle these small cells and have them automatically adapt to the environment? Then you get into some areas that are really around cooperation between base stations, joint resource allocation between the base stations, making sure that you don't optimize one network, one technology, one layer in the network, but you're really hurting yourself somewhere else. So how do you make sure that increasing the power at the macro layer doesn't drown out the micro layers, for example? So I highlighted 3 areas here that I'll talk a little bit more, and those are areas that we actually in the department have some work ongoing. And then beyond just the radio access network, you get into applications and content. So how do I tie the physical and MAC layer, network layers? How do I tie that to applications and content? Are there ways that I can locally cache? How do I do that when I know what the users are interested in, where they are, what they want to do? Can I tie that a little bit more tightly to the network operation? And then finally, there is the buzzword about cloud. Do I want to do all of this the same way that I've done it in the base station with all the processing in the traditional elements, the traditional network elements like a base station controller, or do I just say the extreme view is the radio, the network is really a bunch of antenna and a bunch of radio heads, and I pull everything back into a cloud and then do like essentially a virtual radio access network, and I just have my antenna heads, and I pull everything back, and I do processing there. So there are a lot of people who think that there are efficiencies to be gained there from a CapEx, from an OpEx, even from a green perspective. But that presents challenges because you have a lot of constraints in your wireless network, primarily from a latency perspective. So now you haul everything back to a central point. How do you make sure that you get the fast turnaround, and how do you architect that backhaul network? And there, the cloud here is very different from an IT cloud. I'm really thinking a telco cloud, which has to take the specific telco constraints into account. It's not your Amazon IT cloud, where you do your Amazon purchases in the cloud, where your constraints are very different. This will be a very different cloud. Yeah, kind of a real-time cloud. Okay, so I have a few slides on some of the stuff that we're doing. The first one I want to mention is uplink interference mitigation through cooperation in the radio access network. And so imagine you have a network with only macro cells, and we said there's an evolution towards deploying macro cell, but then sprinkle a lot of these small cells into the network, into these macro coverage areas, and they're deployed at the same frequency band, because ultimately the carrier is limited to particular frequency band, so they want to deploy these small cells in the same frequency band and not separate. We'll get back to that in a few slides, but imagine that for now. So in this chart, we're showing essentially the CDF of the SINR in different scenarios. The black curve is showing the SINR if you only had this macro cell. Now I'm throwing in these small cells, and I don't do anything, and these will interfere with each other. So the blue curve, you're actually paying an SINR penalty because these small cells now interfere with the macro cell and vice versa. So you get this blue cell, this blue curve. The pink purplish curve is if I assume, hypothetically speaking, that I deploy these small cells and I somehow manage to get the interference out completely. Through some magic wand, I manage to deploy them, I get the capacity boost, but without any interference between the small cells. Somehow so this gives you your best case scenario of what you could do without any interference between these small cells. And then the red curve is an intermediate curve where you do some interference cancellation locally at the base station, but not globally in the network. So what we're really saying is, if this is where we are, we want to deploy these macro cells, these metro cells, we take an interference hit if we don't do anything about the interference or any smart management. This is the gap. We could potentially move the CDF to the right, and to the right is better, but this is really the magical solution. So can we come up with techniques that help us improve the SINR in practical scenarios? So one of the things that people do is backhaul, consider all the data from all the base stations. So I think this is uplink. A mobile talks to the base station. You take all the information that the base stations collect from all the mobiles. You send all the signals back to a common data point, and you basically do a joint MMSE processing on a very large vector of data. There's one problem with that in the sense that it requires a huge amount of backhaul. You need really, really big pipes out of the base station to that common processing point, to the point that that's a theoretical exercise. That may work in some greenfield deployments, but practically speaking, you require fiber to every base station. And a lot of these scenarios, these base station locations are where we deployed already 2G when we didn't have the need for that backhaul. So long term, that might be a solution. In greenfield deployments, that might be a solution, but it's not always practical or cost effective. So we're really looking, but that's sort of the best way you can do it if you do some joint MMSE processing, and that usually goes under the name of network MIMO. So what we're trying to do is see if we come up with techniques that give us essentially the network MIMO gains, but don't have the same backhaul penalty. Okay? And what we do is, the scenario here is you have two base stations. You have user A and user B. User B is decoded at base station B, is interfering with user A at base station A, but it's not really a strong interferer. User A is at the edge of cell A, and it's really a strong interferer with user B. So because of that, base station B can actually not decode user B. But base station A can decode user A, because this dotted blue line is weak interference, because this user is much further away from the base station. Base station A can decode user A, And then in the backhaul, I'm sending the decoded information. I'm not sending the raw data. I'm sending the decoded information back to base station B. And now I'm subtracting, essentially, I re-encode the information I get on the backhaul. I subtract out this strong interferer, and now as a result, I can decode user B. So that's essentially the idea behind it. And we have several papers that are published on this. So here's one reference that you guys can look up. This is the only equation in the talk, but I had to put one in. But what I want to show with this is really two things. One is give you a pointer to some problems that if no offense, but I think if I had looked at this problem 10 years ago, even my early days in the labs, I would not have worried about this problem. I would have said, I just want to go for maximum spectral efficiency. I'll work on, network MIMO, and okay, fine, we'll have fiber to the base station. That's okay. I don't have to worry about that. Will just happen. But when you actually think about in practice, then you get into, okay, maybe I shouldn't go for maximum spectral efficiency because that brings about so many other problems. And this is kind of the new twist we put on some of these things. Okay, what does it mean to really deploy this? And maybe if I back off by a little bit on my spectral efficiency, I can still get a lot of gains, but now I make it practical and actually realize the gains. And let me skip this. So this is just one chart to summarize some of the results what I mean about this trade-off. So on the top left chart, showing you the average spectral efficiency. So this is in bits per second per hertz per sector. The light blue is, think of that as current state of the art. So no coordination between the base stations, no interference cancellation, so forth. The gray is what you can achieve with network MIMO. So that's if you had no constraints on the backhaul and you did the full joint MMSE processing. And the yellow one is what we can achieve with this nice scheme. Okay? And of course, you'll have to back off. Right? And the left three bars are with assuming ideal channel conditions, assuming ideal knowledge of the channel condition. You know it perfectly. The right three bars are when we also couple in channel estimation into it, because at base station B, you get the decoded information from user A, but you also have to estimate the channel. So that's kind of this HAB hat. So you have to estimate that based on some pilot signals. And so you do make errors in your estimation, and as a result of it, you don't perfectly cancel out the interference. So there are two messages here. So this graph is the average spectral efficiency, and this is the 5th percentile spectral efficiency, which is also important to look at, because that's really, say, your edge performance. If you're at the edge of the cell, can I give you a boost if you're at the edge of the cell and still give you, essentially give you meaningful throughput when you're at the edge of the cell? So of course you'll need to, you're not getting the same performance as network MIMO, but we actually don't have to back off that much. We still see about a 2x gain over the current scheme without cooperation in the RAN, and we drop maybe 10-15% of performance compared to the maximum we think we could achieve without any backhaul constraints. So that's still a pretty big gain. I know I need to back off from the maximum, but then the flip side is here is this bottom chart shows you the overhead, the backhaul overhead out of each base station, and oh my God, I'm seeing a 40x decrease in the overhead on the backhaul. So now your question is, are you willing to give up a 10% improvement on your spectral efficiency for a 40x reduction in backhaul? Now you still need a big backhaul, but it's not. It's 40x less. So maybe a gigi backhaul or a couple of gigi lines might just be sufficient versus the really big fiber. So this is kind of the trade-offs we're looking at. Now what's also interesting with network MIMO, it's sort of a black and white thing. You do the joint processing or you don't. With this nice scheme, there are different iterations of how many of those strong interference you decode. And it scales and degrades gracefully with the number of interference that you decode. So your backhaul overhead scales with the number of users that you want to decode. So I could back up. This is the maximum gain we could get on the back with the decoding on the backhaul. I could reduce the backhaul overhead further if I'm willing to drop the performance improvement further. So I actually have a trade-off and that I can ride and different operating points that can look at. So so that's one thing that I want to just kind of. I think Nick, you asked me to talk a little bit about how give you some examples of how academic research may be different from Bell Labs research, and how we maybe look at different things and look at different constraints. So this is maybe one example of, personally, I don't think I would have worked on this 10 years ago. It was like, okay. No, the other part is we actually getting traction with this scheme in our business unit, which then brings a lot of other interesting things, that there's still a lot of computational overhead, not backhaul overhead, but computational overhead to run this algorithm. And now you get into how do you deploy this in products. Now you get into these very nice discussions of, here's my latency, I need to schedule these things, here's a latency budget, here's a MIPS budget that you have. How do you actually make these trade-offs? And again, I would never have thought about those things, or you don't even know that. So it's also kind of nice when you then, it's nice to talk about nice, when you talk about, when you move things into the business unit, that then you get into this discussion of how do I actually make it practical. And now we have discussions of how many of these strong interferes can I decode as a function of the processing capabilities I have on the chip. And I challenge any of you to have thought about that before I told you, right? That's like a really kind of, Bert, you probably would have thought about it, but because of your background, right? And so that's kind of where it's nice to think about the bigger picture and not just optimize in one dimension, but you really have to optimize in multiple dimensions at the same time. Okay. Oh, wow. Okay. I'm talking too much. Okay, so let me go maybe a little bit faster on some of this stuff. So some of the other things we're looking at, I said, imagine the scenario of macro cells and small cells, but deployed in the same frequency. Now, there are different frequency deployments you can have. You can say, I own two frequency bands, F1 and F2, and I deploy the macro cells for F1 and F2, and then I deploy small cells only, deploy small cells in F1 and F2 also, and I have the full interference. Or you say, I'm only using F1 for macro cells, I'm using F2 for small cells. Carriers don't really like that because they feel like they're only using half their spectrum. But at the same time, if you do that, you don't get the interference between your small cells and your macro cells. So is that really bad or is it really good? You can think about straddling these small cells, so you use half of F1, half of F2. So this is the strict reuse. This is the full reuse, where you go at full power on the small cell and the macro cell in both frequencies, but now you fully interfere. So one thing that we call soft reuse is we're actually looking at the macro and the small cell both using both frequencies, but we power modulate these different carriers. So you may have on F2, the macro cell and the small cell use the same or similar transmit power. So they do interfere, but I'm deliberately setting up the interference and controlling it by assigning different users to different frequency bands. On F1, I modulate my transmit power, so I still have the high transmit power on the macro cell, but now I go really low power on the small cell, and maybe by managing that, I don't create as much interference on F1. I can assign some users to F1, I can assign other users to F2, and I can play these games of how do I choose my frequency plan, how do I choose my power strategies to get the maximum performance out of it. And all of these power levels will then really depend on what is your current situation in network, how many users do you have, are they mobile, are they somewhat stationary, what are their throughput requirements, how many do I have, and so forth. And that brings you then back to the self-organizing algorithms of, you can come up with a strategy and you optimize the transmit powers, but in reality, you'll have to dynamically configure these based on some real-time measurements in the network. I'll leave most of these slides, if not all of them, with you afterwards. So this is just a quick chart to say that you can get some gains. Again, we're plotting the mean and the edge throughput. So we're seeing that you can get, so this is throughput gain relative to no small cells. So you can, you see with a full reuse, you do get the big mean gain, but you're really hurting yourself on the edge, because that's really the interference limiting you. If you do this soft reuse with the power modulation, we don't quite get the same average throughput gain, but now we're not really hurting ourselves on the edge as much, and we actually do get a benefit on the edge. So again, it's some of these trade-offs that you play, and really not just looking at interference, not just going for maximum performance on one dimension, but really kind of looking at different dimensions together. This one I want to mention, it goes in, I guess the three topics on the uplink interference cancellation, the soft reuse, and this macro cell anchored radio, they go progressively more disruptive and progressively more long term. This one is where you say, why do I, if I have small cells and I have macro cells, why do I have to be connected to one and only one? Maybe I should be partially connected to the macro cell. Maybe my signaling is to the macro cell. That's how I maintain my lifeline to the network. But when I need a capacity boost because I'm running a big video application, then I'm connecting to the small cell purely on the data plane. So I'm really looking at new architectures where I separate signaling and data. And so we've come to this problem from an interference perspective, because your power level is driven by to what base station you signal. That sets your link budget and your power level. So we've come to this from managing interference and driving edge rates up. Other people in the company have come to this same kind of architecture from a green perspective, which is kind of interesting that this might also be a greener solution. I'm trying to get my team working on this, working with the other team working on this from a green perspective. And so that's kind of an interesting thing where you have same idea coming from different perspectives. So maybe this is a winner because of that. I don't know yet. This is still a little bit early, but we have some initial results again published on that. I really have to speed it up. But so far I talked about really making the bit pipes at the air interface as big as you can. I'm saying there are these different layers, there are these different technologies, they interfere with each other, and I'm playing smart games to make the pipes as big as possible by reducing interference, canceling interference, and so forth. There's another dimension of, if I have these certain bit pipes, how do I use them in the most efficient way? And this is really, if you think about your device, you may have a 3G, a 4G, and a Wi-Fi interface. You're running a particular application. Should you connect your device on 3G or 4G or Wi-Fi? And so this is where we look at really the resource allocation and the assignment of users and flows in the network to the particular layers in the hierarchy. Some of the work has been done, and there are a lot of people actually looking at that, but we're trying to take another angle to it by coupling maybe your willingness to pay, maybe coupling the type of applications you're running. And you're the same person, you're in the same location, it's the same time of day, you have the same device, but I need to send a presentation to the president of Bell Labs. I'm about to get on the plane to China. It really has to go out right now. I'm willing to pay extra. I want the high capacity link. I want the boost. I'm willing to pay extra. I'm sending a Facebook update. Maybe I don't want to go on the Wi-Fi link. That can wait. I'm not willing to pay extra. You can give it to me for free or for low price. I'll take it. But how do I play? I'm still the same person at the same airport at the same time. But depending on what I'm doing, my profile, my preferences may be different. My willingness to pay, my requirements may be different. How do I make these intelligent decisions? And this is just taking my preference into account. Now you have to get real-time information from the network to say, I'm sorry, you cannot go on 4G. That's like totally congested with people that are willing to pay more for it than you. So how do I take, again, it goes into the SAN space, and how do I take real-time information out of the network and then make intelligent decisions to really optimize the performance for everybody by assigning people to the right layer in the network. So this is just kind of the cartoon picture of, you have the different layers, you have different measuring points in the network, you get information out of the network, you make these intelligent decisions, and then also you have to execute on those decisions. And maybe you're on one link, something happens in the network, or you move out of the Wi-Fi coverage area, you have to be switched over to another layer in the network. How do I make sure that happens seamlessly without you having to restart your application, without your video quality? Well, your video quality might change, but without the video link breaking. How do I make sure that that's happening seamlessly? And if you want to go really far out, how do I make sure this happens across operators? Maybe Verizon or AT&T or Sprint are not the cheapest one. I can't switch right now. I have my Verizon coverage, and that's why maybe I want to switch them because they offer a better deal on high throughputs right now. How do I make that connection and that seamless transfer between operators who don't necessarily have agreements and trust relationships? So we have some ideas on that also, and there's some kind of nice stuff and to think about there. Okay, so let me talk a little bit about green, and go back to another dimension about the networks that I think will be more and more important. Just some numbers to get us started. Right now, you have about 5 million towers in the world, on average consuming maybe a kilowatt. So when you equate that out, that's about 9 Hoover dams. 78 million tons of CO2. There are different ways you can play this game, but the equivalent of 15 million cars and so forth. So there's a huge amount of power being consumed in the wireless network, and this is the picture today. So if you remember the growth that we talked about, 30x in 5 years, that is not the power consumption in 5 years, that is today. So this is only going to get worse. Oh, and by the way, there's still 5 billion people who don't have broadband, so that factors into that. So this could potentially be a really big problem. It sounds a bit like the sky is falling right now. It's not necessarily a big problem today, but if all the predictions are somewhat close, this could be a big problem in the future. And none of us, equipment providers, service providers, and consumers, we don't want this to become a problem, because that will really limit what we can do with the devices, how we use the devices. And if you believe the story about the applications and the devices at the very beginning, you don't want anything to limit you in terms of being able to do that. So this is just to break it down a little bit. This is purely looking at the radio access network, how the power consumption is broken down. And the message here is that the base station is by far and large the biggest consumer of power in the access network. Different estimates are between 70 and 80% of the total power consumption in the wireless network is on the base station side. You look at utility bills for some of the operators, that the electric bill could be between 10 to 20, sometimes up to 40% of their OpEx. So depending on who you look at, it may not be a very big deal. It could be sub 10% of their overall budget. I'm sorry, their overall 7 to 10% of their overall budget is their utility bill. Sometimes could be up to 20, 25%. So CapEx is still dominating, but with some of the trends of equipment maybe becoming more commoditized, plus the cost of power is expected to go up, you can certainly expect the trend to be maybe not reversed, but at least going into the unfavorable direction for the utility bills. Okay. So let me skip this slide. This is maybe one way of thinking about, maybe I shouldn't skip it, because if you look at it afterwards, it's hard to read. So you want to read this slide from the right up and then to the left. So the right side is plotting basically think of P out as the RF power that you have to generate for a certain amount of traffic that you want to send through the network. This is state of the art. So this is your state of the art curve of, for a certain amount of traffic you want to send, you need a certain amount of output power. So anything you do on the efficiency side of reducing the RF power will lower this curve. And you can look at it two ways. You're saying for the same amount of traffic, I need less power, or for the same amount of power, I now manage to send more traffic. And that's maybe the business way of looking at it. I don't have to spend more on my utility bill. I don't have to use more power, but now I can actually handle the traffic growth. The green version is saying I send the same amount of traffic, I just use less power. But those are two sides of the same coin. So now you have a certain amount of output power. That's your RF power. How much power do you actually need to put into the base station? You have all your overheads from your cooling, your power supplies, your processing, and so forth. So for a certain amount of output power, you need a certain amount of input power. So this is really the one driving your utility bill. Right? So any efficiencies that you get on the equipment will move this curve to the left. So you're saying for the same amount of output power, I need less input power. So that's the gain you get from the hardware side. This is showing the gain you get from the network side of doing more efficient packet processing, more efficient network architectures, anything you put to sleep, and so on. This is not about the hardware in the base station itself. That's the right side. So that's this gain. Here's the gain you get from doing more efficient wireless pieces. Here's more efficient hardware. And then you get some combined gain where saying for this amount of traffic, now I only need to inject this much power to the box versus this much power. So that's maybe a way of, now this is a cartoon picture. What you really want is what are actual curves of current P out versus traffic, and how do different ideas, different green technologies, how do they actually change these curves? And then it's really important to look at how ultimately these curves then map into any gains that you can get. Right? So just real quick, I have about 3 more slides or so. Just no results, no details, just highlighting some areas that we are doing inside Bell Labs, and we're also part of a consortium called Green Touch. So some of this is ongoing activity. There are some initial results, and some things are still fairly early stage. So there's definitely opportunity to contribute and collaborate on things like this. But they generally fall in the category of deployments, anything looking at relay nodes, looking at these, again, are small cells more energy efficient than macro cells? These heterogeneous networks, everything I said before, you can translate throughput gains into power gains also. So it's looking at the network architectures. How do we manage the networks more efficiently? Maybe if I don't have as much traffic, maybe I should turn some of the frequency bands off. Maybe if you think back to the previous example about soft reuse, maybe I don't use F1 and F2 and split my traffic between the two. Maybe I turn F2 off, save power on the equipment there. Then you have everything that goes with dynamic resource management. It's energy efficient scheduling, sleep modes, bandwidth adaptation. You have these diurnal cycles in the traffic. How do I make sure that the resource utilization matches the diurnal cycles of the traffic? And a lot of times the resources are completely turned on independently of the traffic load. So you want to get essentially an energy follows load profile that as your traffic changes, you want to match the utilization of resources to your traffic. Different antenna technologies. This is a project in Bell Labs. It's also in Green Touch about massive MIMO. So we're talking about hundreds of antennas versus 4 or 8. This gets more into the cloud space of how do I just distribute these antenna and then I backhaul everything to a central processing unit. Does that give me green benefits or not? This is the one that I mentioned earlier. And again, these go a little bit, as you go through the slides, they get progressively more disruptive and progressively more long-term. So this is a project called Beyond Cellular Green Communication, where you separate your data plane from your signaling plane, and you have these small cells. You connect to the macro cell for signaling and for your lifeline. If you have a data session, you connect to the small cells. The coverage of these small cells is fairly small, so you may not have a lot of users in those small cells. If there's nobody, you can put them to sleep. You maintain your signaling connection so I can get paged. Yeah, the network can wake you up if there's traffic for you. And if you move, you trigger fewer handoffs because you remain connected to the macro layer, so you don't have this large frequency of handoffs that drop the calls. So again, this is fairly early, but there's some interesting challenges on even does this make sense, and then what are the underlying challenges to make this kind of architecture happen, and that's obviously not standards compliant right now, so that's much more disruptive. Okay, so I'll stop on that.